Hello everyone, we are the Triple Jump team, and our our team project is the predicting the click-through rate of sponsored search. We choose the topic for two reasons. The first is that the problem itself is interesting and important. The search advertising is actually the main source of revenue for the internet industry, and actually the predicting click-through rate is the one of the key technology behind. And the second reason is that this problem is the topic of this year's KDD Cup contest. So we have a very good new data set, which is public, which is real and large scale, and it provides a lot of interesting features. So we think it is a good opportunity to explore deeper into this problem, and possibly we can beat the state-of-the-art approaches so far. So first, let's look at the background. Suppose that the user submits a query to the search engine, and the search engine returns a search result page to the user. So as this image shows, besides the search result links that the search engine returns, there are also up to 3 advertisement items at the top. And what we want to do is to predict whether or not the user will click on each of these ads. So based on which information we are doing the prediction? There's 3 sources of information, basically. The first one is the query, which reflects the user's search intent and information need. And the second is from the advertisement itself, which include the title, the keywords and descriptions, and the advertiser identity, and so on. And the third information is from the user profile, which is available to the search engine if the user is logging in when he or she is doing the web search. And this kind of information may include the gender of the user and age or other personal information that the user provides to the search engine when he or she registered the account. So basically, the clicking prediction problem is a conditional probability model. We want to predict the probability that the clicking event happens under the condition that all this information we have. So as the first step of our effort, we surveyed the published literatures, and we summarized it and implemented some of the state-of-the-art approaches. The first and the simplest one is the empirical counting approach, which means that we predict the CTR, or CTR is the abbreviation for the click-through rate. We predict the CTR of every AI as the empirical CTR in the training set. It's roughly an empirical CTR because we also use a constant beta factor as a smoothing factor, so that even if the ads in the testing set does not appear in the training set, we can still give a reasonable prediction using a global parameter P, which is typically set to be the overall empirical CTR over all the instances in the training set. So the advantage of this approach is that it is very simple, so the computational cost is low, and it is very easy to be parallelized because counting can be very easily fitted into the MapReduce framework. But the bad thing is that it is too simple, so it uses very limited information. Actually, it uses no more information than the ad's identity. We can further improve this model to be a position model, which is based on the observation that the user browsed the web page from top to bottom. And by this pattern, the ads ranked at higher positions has a higher chance to attract the user's attention and the user's click, even if this ad is not as relevant as the ads ranked at the lower positions. So we formalize this observation as the position bias and use it as a discount factor in the formulation. So in particular, our formula is that the CTR of an ad is defined as the product of 2 terms. The first one is the position bias indexed by the position of the ad J, and the second one is the relevance, or it is a matter of the ad quality. And we use the expectation maximization algorithm to derive the optimal values of these 2 classes of quantities, the position bias and the relevance. So the good point of this method is that since we consider the position bias, we can get a more accurate estimation to the relevance or the true quality of the ads. And moreover, when we do the prediction, this position bias factor can provide a better discount that can distinguish the different average click-through rates at different positions. So we have a further improvement in prediction. But this model is still limited because it does not consider any information in the user profile or any text information. The third method is the classical logistic regression. So in this method, we summarize the one impression of, we are given one impression of the advertisement, and we summarize all the information we have to a feature vector theta. And we multiply this vector by a weight vector w, and then using a logic link function to model the CTR of the S. Since the logistic regression has been well studied, so there's an online optimization algorithm which is very efficient. And another good point is that it allows us to incorporate all the information we have into the model because we can put everything we have into the feature. But the problem is that if we put everything we have into the feature, then we will have a very high-dimensional feature vector, and this will cause the problem of overfitting. And the curse of dimensionality will cause other problems, but it's beyond the scope of this talk. So in order to partially solve the overfitting problem, we can switch from the logistic regression to the probability regression. So the point is that we replace the logic link function by probability link function, which is the CDF of the standard normal distribution. You can see from this figure in the corner that the shape of the two link functions are quite similar. But the interesting point about the probability link is that it has a close relation to the Gaussian density. So we can use a variational Bayesian inference algorithm to approximately derive the posterior distribution of the weight vector W given the training set. So the advantage of doing this is that we can avoid overfitting by the posterior Bayesian posterior, because if the confidence level of the estimate is low, then it will introduce a large variance, and this large variance will have an effect of adaptive smoothing. But the bad point is that because the algorithm becomes more complicated, there's no guarantee of convergence, and because it is an approximate algorithm, we cannot guarantee that it always get to the right point, and it is also hard to parallelize. So this is what we have so far, and this is also the foundation that we will build our own works on. And before stating our future plan, let's take a closer look at the data. Our data is from soso.com, which is the third largest search engine in Chinese market, and it consists of 600,000 ads which are presented to the user for 235 million times. And it also have associated queries with 24 million associated queries submitted by 23 million distinct users. And they have three characteristics of the data. The first is that the data is long tail, which means that nearly 50% of the data, nearly 50% of the ads has at most 10% impressions in the training set. So this is a challenge because we cannot use traditional statistical approaches on this ads because of the small number of impressions. And the clicks are also sparse, which means that more than 60% of the ads does not receive any click in the training set. So it is a challenge to guess what is the real and actual CTR that this ad should have. And third is that it's the position bias. So without surprise, we see that different positions have significantly different average CTRs. And this difference is partially due to the diversity of the quality of ads at different positions, and partially due to the user's browsing pattern. So we have to model these two effects respectively and precisely. So in our preliminary experiment, we have implemented two of the approaches we mentioned above, which is the empirical counting and position model. And we compare them to the baseline, which is just predicting everything in the testing set, every CTR in the testing set by 0.038, which is the global overall empirical CTR in the training set. So the experiment shows that our approaches already outperforms the baselines consistently and significantly. But there are still more room for further improvement because this method has only used very limited information. And this is our future plans. This is a straightforward plan. So in the modeling side, we are going to incorporate the user profile information and the text information into our models. And this involves the works of personalized modeling and topic modeling. Although there are a lot of previous works on these two fields, but it still remains challenging and open to integrate these works into the field of click modeling. And on the algorithmic side, we are also considering to explore deeper into the scalability of the algorithm because as the model being more complicated, our algorithm will have a big issue in how to fit into the big data and how to fit into the distributed computing environment. And so we will have to propose new algorithms and analyze their convergence properties in theory. So that's it. Thank you.